হ্যালো স্যার, আসসালামু আলাইকুম।
আসসালামু আলাইকুম, কি খবর?
এই তো স্যার চলছে।
ভালো আছো?
জি স্যার।
How is everything? How's your family and everyone?
Everyone safe, sir. How about you?
I'm doing fine, thank you very much. Alhamdulillah.
Okay, sir.
আচ্ছা, তাহলে বেসিক্যালি আমাদের স্পিকার অর্ডার ঠিক হয়ে গেছে। তাহলে সোহেল রহমান স্যার উনি আগে বলতেছে ফার্স্টে।
জি স্যার।
আচ্ছা, তারপরে আচ্ছা আমাদের যে থাইল্যান্ড থেকে যে স্পিকার আছে ওনার নামটা একটু প্রনাউন্সিয়েশনটা, ওনার ইউনিভার্সিটির প্রনাউন্সিয়েশনটা একটু আমাকে কনফার্ম করতে হবে, কারণ ওনার বায়োগ্রাফি আমি পড়বো। তো আমি নামটার উচ্চারণ আর ওনার ইউনিভার্সিটির উচ্চারণটা ভুল করলে দেখতে খারাপ লাগে।
স্যার উনি মানে আমি ওনাদেরকে মেল করছি যে অ্যাটলিস্ট 15 মিনিট আগে জয়েন করার জন্য। তো আপনি আস্ক করে নিতে পারেন, কারণ আমিও অ্যাকচুয়ালি ওনার সাথে শিওর না আর কি। বা শাহিন কাছে স্যার হয়তো কনফার্ম করতে পারবেন।
ডক্টর সুপাভাদি আরামভিত, এটা তো পুরো নাম অ্যাটলিস্ট লিখে যেটা পড়ি। আর 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 ইউনিভার্সিটি আলহামদুলিল্লাহ কি কুলাংকংকর্ন ইউনিভার্সিটি। সো আমি শিওর আমি এটা মেস আপ করছি, শিওর। তো এটা 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 জানতে হবে আর কি।
জি স্যার, সমস্যা নেই।
ওকে, ঠিক আছে।
হ্যাঁ, আমি আছি স্যার। আসসালামু আলাইকুম। হ্যাঁ,
ওয়ালাইকুম আসসালাম।
আমি আছি, সমস্যা নেই। লাইনে থাকেন, আপনি আপনি হাতের কাজ কিছু সেরে নিতে পারেন। আমরা
আমি লাইনে আছি,
ঠিক আছে।
আমার গলা ঠিক মতো আসতেছে, ভয়েস
ঠিক আছে, গলা ঠিক মতোই আসতেছে। লাঞ্চ করেছেন? লাঞ্চ করেছেন?
আমি লাঞ্চ এখন আমি বিকালে একটাই খাওয়া খাই, কেন এখন লকডাউনে তো বাসা বসে আছি। বেশি খেলে এমনিও মোটা, আরো মোটা হয়ে যাবো। সো খাওয়া কোয়ান্টিটি কমাই দিছি।
এক্স্যাক্টলি।
না হলে মানে বয়সও বাড়তেছে, এমনিও মোটা সোটা মানুষ, আর ভোরতে হলে আপনি
সমস্যা সেটাই। ঠিক আছে, ইনশাআল্লাহ আমি একটু বাচ্চাকে একটু খাবারটা বেড়ে দিয়ে আসতেছি।
শিওর।
জি, থ্যাংক ইউ।
Yes, sir.
Hello, moderator.
Start করব?
Yeah, please.
Okay, I start. Hello everyone. Assalamu alaikum. Today is 31st May 2020, Sunday. On behalf of IEEE Computer Society Bangladesh Chapter, me, Dr. Mohammad Ghulam Kibriya, Associate Professor at ULab, and Dr. Mustafa Habib Choudhury, Associate Professor at IUB, welcome you to the second session of the International Lecture Series titled Fight Against COVID-19 Using Machine Learning. The first lecture of the webinar that was held on 17th May met with a huge response. IEEE Computer Society Bangladesh Chapter, in collaboration with Team Spark, is back with the second lecture of the series, powered by IEEE Computer Society BUET Student Branch Chapter and IEEE Computer Society BRACU Student Branch Chapter, along with Humanitarian partner IEEE Computer Society Bangladesh Chapter HAC. We know at this pandemic, hundreds of research teams around the world are combining their efforts to collect data and develop solutions. Application of machine learning in this data will help understanding virus better, identifying who is most at risk, developing drugs faster, finding existing drugs that can help, predicting the spread of the disease, mapping where virus come from, predicting the next pandemic, etc. To share the knowledge and ongoing research around the globe, IEEE Computer Society Bangladesh Chapter organizes 4 lecture series. Today, in this second session, we have 3 intellectual speakers, including Professor Dr. Mohammad Sohel Rahman, Dr. Supavadee Aramvith from the Department of Electrical Engineering of Chulalongkorn University in Thailand, and Dr. Mohammad Enamul Haq Choudhury from the Department of Electrical Engineering of Qatar University in Qatar. Today we have professors and students from different universities, industry representatives, IEEE Computer Society EXCO members, and other respected participants. Welcome everyone. This webinar is broadcasted to Facebook page of IEEE Computer Society, IEEE Computer Society BUET Student Branch Facebook page, and IEEE Computer Society BRACU Student Branch page, Facebook page. Now, I hand over the mic to Dr. Mustafa Habib Choudhury to continue. Thank you.
Thank you very much, Dr. Kibriya. First, I'd like to thank all the participants and the organizers for organizing this session today. We hope that this session will be very informative and exciting. Without further ado, let me first introduce you to the first speaker of today's session, which is Professor Dr. Mohammad Sohel Rahman, who is a professor of Computer Science Department of BUET, the premier university in the field of engineering and technology in Bangladesh. He has worked as a visiting research fellow of King's College London in the UK from 2008 to 2011, and again as a visiting senior research fellow at the same institute during 2014 to 2015. He is a senior member of both IEEE and ACM, and a member of American Mathematical Society and London Mathematical Society. He's a peer review associate college member of EPSRC UK. Dr. Rahman received different scholarships and fellowships, including Commonwealth Scholarship, Commonwealth Fellowship, ACU Titular Fellowship, University College London Big Data Institute Visiting Grant. He's also a recipient of the Bangladesh Academy of Sciences Gold Medal and UGC Award. He has led research and development projects funded by British Council, UGC World Bank, and BUET. He's currently serving as an academic editor of PLOS One Journal and associate editor of BMC Research Notes Journal. He has also served as a program committee member in a number of conference series of international repute. He has collaborated with eminent scientists and researchers from both home and abroad. Dr. Rahman regularly writes reviews at Mathematical Review and Computer Review. And Professor Rahman is also the current Vice Chair Technical of IEEE Computer Society Bangladesh Chapter. Without further ado, I'd give the floor over to Professor Sohel Rahman to please present his speech to us, or talk. Thank you.
Thank you. Thank you very much. Can everyone hear me? So I'm going to share my slide. Okay. So first of all, thank you very much for inviting me in this nice international seminar series. And I'm humbled to be in the panel of speakers where we have like eminent speakers from Thailand, Professor Supavadee, as well as Dr. Enamul. So, and I also thank the moderators for giving a very nice introduction and very generous introduction about me. So I'm going to talk about something which is related to COVID-19, and my title is, as you can see, how can we fight against COVID-19? So I want to first define what do I mean by we, and this is relevant, particularly in the context of Bangladesh, where we all want to get involved in supporting our country in COVID-19 research, but we do not get enough opportunity, at least in my humble opinion. So the first thing that I'm going to try to define is what I mean by we here. We all know that COVID-19 is a pandemic, and this is affecting Bangladesh as well. The numbers that we are hearing for the last few days are alarming. We do not know what is coming and so on. We are trying to make us ready to combat this at the policy level as well as the personal level. But we all are I should say we are very, very cautious about how to interpret things and how to do things. So overall, of course, the fighting is going on between the public as well as the front and emergency workers and doctors as well. And here we have the academicians and researchers. Probably we're looking forward with many research questions, and we have students who now have free times because the students, they don't have academic activities going on that much, especially the public university students, the best students of Bangladesh. And we have the policymakers. In general, I will give you an example of United Kingdom. The situation should have been like something like this. In UK, the government created an initiative called RAMP initiative, where they send a call for support to all the academicians and researchers and the students as well, and asking them how they can provide the support. How they can provide the support, they can provide logistics, they can provide any previous models they have worked on, they can provide any previous predictive models, classifiers, etc. that they have worked on, which can be used in the context of COVID-19 and so on. Also, they asked for support from the institutes, whether they have computing facilities and other things. And in response to this support, there were overwhelming response, in fact. And from the whole situation is coordinated by the Royal Society, and they are trying to get the best resources out of those and trying to combat COVID-19 in different angles, in different dimensions. So ideally, we should have done something like this, but unfortunately, we don't have something like this in our country. And this probably put many of the researchers in a frustrating position. I want to just point out that we shouldn't be frustrated and we shouldn't be disheartened. And we have to understand that we have many limitations. We cannot do what UK could do and so on. So whatever position you are in whatever capacity you can do, we should try to do whatever we can. So this is the situation. I would say by we, I mean the academicians and researchers and the students, particularly in computing area, because here we are as far as I know, most of us are from computer science background and so on. And we hope that if we can find something useful, we can place it to the policymakers, and the policymakers could use that for the sake of the good of our country. The problem that we have is the RAMP initiative that I mentioned, there the government is providing the data to the researchers to work on. Unfortunately, we don't have that system in place, at least not for the Computing Science Society as far as I know. So whatever data we have from international community, from the public sites and so on, we should use those data, whatever facilities that we have, we should use those and leverage those and use our potential, the exceptionally talented students of our country, particularly in the CS domain, and exploit their talent to find something interesting. So this is the basic background that I'm going to discuss. And now I come to the point, what can we do now? I have defined what we are. So there are a lot of research opportunities, and I think everyone are more or less familiar with these things. Like we have immunology, where we can work, and we have like public health area, we have like clinical researches, we have research questions in social sciences as well. And of course, we have many questions in computing. And in fact, as it turns out, in every aspect, we have computational questions. So computing is almost everywhere applicable. We have data analytics problems, statistical and machine learning and so on, everywhere, in immunology, in public health, in social science, in clinical research, and in computing as well. We have computational biological questions. We have like biomedical science and engineering questions. We of course have modeling questions. We want to, in fact, the moderator, in fact, nicely introduced the whole situation. We want to predict where the COVID-19 is going. And when will the second wave come, for example, where the first wave has gone, and so on. So there are modeling questions. We want to provide tools as well that other researchers from other communities can use and so on. And of course, we have many ICT applications. So this is basically not only research, it is research and development. We all talk about contract tracing app, which also helps in research as well. And this is a direct application of ICT, right? So all these things are very, very interesting and unlimited scope. They provide us unlimited scope for doing research. And we should take the opportunity to do something using our talent, using our local talent, using collaboration with international researchers and so on. I will come back to this slide towards the end of this talk again. So in today's presentation, I would like to show you that we have tried to do something where we have touched data analytics, that is machine learning in particular, biomedical science and engineering, computational biology, as well as we have provided a tool. The name of the tool is COVID-19 base 1.0 for now, which we say it is a comprehensive knowledge base for coronaviruses. And we have used machine learning techniques and so many things here. I will try to explain why and how we have used that. So the motivation, what is the motivation of this COVID-19 base? The first question anyone would ask if he wants to work on COVID-19 is, where do I start, right? Where do I get all the information? Where do I get the background and so on? So this is the very first question. So we were motivated to provide a starting point for the researchers. This was our first goal, to provide a starting point that you should start here. This is a tool, this is a website where you will get, hopefully, whatever knowledge that you need for your particular research, okay? So this was our motivation. And what we have applied is that we try to highlight the biomedical entities related to COVID-19. We have tried to apply natural language processing. It is based on literature mining. We have highlighted those biomedical entities, and we have made it available free for everyone at a public as a public web page. Now, what are the entities that we have used here? So these are the main entities that we have tried to get out, like disease, drugs, genes, long encoding RNAs, messenger RNAs, and of course, proteins. So these are the things that we have tried to identify that are related to COVID-19 and related diseases. And after we have identified these entities, we have tried to find out the interactions and associations between these entities. So we try to identify disease-drug interactions, disease-gene interactions, disease long encoding RNA interactions, messenger RNA interactions, as well as the drug-protein interactions. So this is the main theme of this particular work. But the problem is, all these things usually need manual curation, but we don't have that much time. If you want to make a comprehensive database for this one, then it might take 1, 2, 3 years. to identify all those interactions and so on. So this is where the machine learning, NLP, and all those things come about, okay? So we want to infer the interactions and associations, but at the same time, because we are not doing it completely through manual curation, we want to evaluate how confident we are when we identify a particular association. Also, we want to identify what are the side effects of a particular drug that we find useful, probably useful for COVID-19 and so on. So again, the question comes, why do we need to evaluate? Because we have applied machine and other automated tools which cannot be 100% confident, which cannot be 100% particular association. And someone, any researcher from public health, for immunology, for vaccine development, drug development, he should come to our website to have a as a starting point, as I was mentioning before, try to identify the biomedical entities that are related to COVID-19 from the literature, and then check what sort of confidence score we are mentioning. So if it is with very high confidence, that is one thing. If it is with very low confidence, then he should investigate more and so on. For each association, for each drug we have identified, we have also give a pointer to the main source. So anyone who is interested to start working here, he can also check the source and verify whether our inferred association is going to give you a very brief glimpse of what we have done here. And the main reason for this is to entice you, to encourage you to do this sort of work as well. So the first thing that we had was a Kaggle dataset, which was called COVID-19 dataset. It was based on PubMed, bioRxiv, and medRxiv papers. There were more than 44,000 papers from more than 3,000 journals. And basically, this particular dataset searched for different terms like COVID-19, coronavirus, and different versions of these sort of searches. Also, it searched for previous coronaviruses, so SARS and MERS and so on. And to get the biomedical entities, we used some well-known databases as dictionaries. Like for gene, we used HGNC database. For miRNA, we used MIR-base. And for disease, we use disease ontology database. For drug, we use drug bank database. And for side effect, in fact, we completely dependent on another website, which is called CIDR. So these are the main two materials, the main two sets of materials that we have used. This is the basic methods. We basically extracted disease-drug interactions. Similarly, we extracted disease gene associations. The drug-protein associations are also done in the same way. And finally, we extracted the side effects. I'm just going to describe a little bit about the first two steps, which the others are almost similar. So this is the first step. We want to extract the disease-drug interaction. So first, we extract the disease and drug names. And for this, we simply use a dictionary-based approach. We just find the disease and drug names present in the literature meaning the COVID-19 data set. After we extract the disease and drug names, we try to extract the disease-drug pairs. So we collected all the sentences that contain this disease-drug pair. So it's a co-occurrence-based approach. But unfortunately, there could be many anomalies. So what we have done is we have applied a unsupervised anomaly detection, where we have, in fact, employed this version K-means clustering algorithms. So those of you who have machine learning background, I think you know how K-means clustering works. Can you hear me? Hello?
Yes, we can hear you properly.
So you probably have a very good idea about K-means clustering. So what we did was we made unsupervised clusters. We had two clusters. The cluster that had very small samples, we assume that this is the cluster of anomaly, and we decided to discard that. In our case, we had only a cluster of only 161 instances. So we also manually checked some of those 161 instances. So we were pretty confident that these are the main anomalies from the extracted disease drug pairs. and we decided to discard these anomalies from the rest of the pipeline. So then we needed to understand whether a particular association is positive or negative. For example, you know about remdesivir. This is a drug that has been being tested with many positive results. And whenever in a literature, a drug and disease is mentioned, it might be because someone is mentioning that this drug is not useful, or someone is mentioning that this drug is useful. So to understand that, we applied sentiment analysis. Again, those of you who have good machine learning background, we know that you know how it works. So we use a pre-trained model, which is widely known as the text blob model. You can search for it and you can get this. But the problem is, this is a pre-trained model. And because this is a pre-trained model, this is trained on a different data set. We don't have a ground truth here. So we also wanted to have another sort of step in our pipeline, which is an unsupervised model. So in this unsupervised model, we again apply the k-means clustering, and where we try to divide it into two parts, where we particularly look for some positive words. We try to identify some positive words from the literature, in the biomedical literature, where people uses these sort of words to mean positive things, and some negative words to mean the negative things. So this is unsupervised model. So from this text blob model, we have a result. From the unsupervised model, we also have a result. These two results, these are two scores, polarity scores and sentiment score. These two results, along with the distance between the drug and disease pair within the document where the association has been extracted, these three have been taken as features for another neural network model. But for the neural network model, we had to have a data set, right? So we manually curated 200 associations, 200 interactions with the help of biomedical people. We have them as our collaborators. So with these 200 data, we trained the neural network model. The neural network model was taken a model which was, it is a 3841 model, a deep neural network model, which have been proved to work on a limited number of data in the literature. So we have used that data, nothing novel in it, but we have used that model, and we have used these three features using that 200 strong sample size as the training set. We got, in fact, around 75% testing accuracy. So with this accuracy, we decided that, okay, for the first version of COVID-19 base 1.0, we can provide these as a starting point for the researchers. So we provide the label, so whether a particular association is positive or negative, and we also provide the confidence score, whether it is 75% confidence or it is 90% confidence, and so on. Similarly, we also have the almost similar pipeline for the disease gene RNA extraction and association. For the extraction part is easy. We take the dictionaries and we extract the names. For the association, we have used a word-to-vec model, and from that we created a vector. And from that vector, we have used the concept of cosine similarity. Again, this is a well-known metric. There's nothing new from our side. So we have used the cosine similarity, and here we had a gold standard data set, which is called DisGenNet. Unfortunately, DisGenNet does not have all the extraction, all the associations that we have been able to extract from the literature. We had only around a few common, maybe around 2,000. I forgot the actual number, which are common with DisGenNet. So we use these common values and our cosine similarities to get an idea about what should be the scores for medium, high, and low confidence values. And this is how we decided on the confidence level for the association or interactions for disease and genes. So these are the two main pipelines that we have used. The other extraction, that is other association that we have extracted, basically follows one of these pipelines. And then we have found out 1,811 drugs, 1,219 related diseases, 1,703 genes, and a number of LNC and miRNAs, and proteins, 70 related proteins. But more importantly, we have found these associations. So 12,753 disease drug associations. Among them, according to our pipeline, more than 11,000 are positive and 1,200 are negative. We have found more than 25,000 disease gene associations. Among them, 1977 are verified. This is from Disease GenNet, as I was mentioning. 40, we could call them with very high confidence, more than 15,000 with medium confidence, and slightly less than 8,000 with low confidence. And similar results we have got for the other cases as well. So the two interesting case studies that I'm going to just discuss here very shortly, that we have, I just mentioned about remdesivir, as well as we know about hydroxychloroquine. That these two medicines, these two drugs are the most well discussed drugs during the COVID-19 pandemic. And as it turns out, through our automatic labeling, remdesivir got 75.86% confidence, positive confidence. And we all know now that there are many trials going on with this particular drug. And as for hydroxychloroquine, for this, our confidence level was not that high. It was around 60%, but it was positive. But probably more importantly, we have identified more than 111 side effects for hydroxychloroquine. So the point I'm trying to make is, anyone who wants to check whether a particular drug is drug could be interesting from the COVID-19 point of view, or any viral, antiviral drug point of view, this could be your starting point to check whether this sort of information is already available in the data, in the literature or not. Okay, so we have to give some disclaimers as well, because we have worked with limitations. We didn't have time, and this is why we went for an automatic pipeline. So due to the inherent limitation of the methods and approaches we have adopted, we cannot get an error-free output. So this is why we have provided the confidence level. Anyone can check whether we are very confident about it. Not only that, we have provided the link to the source manuscript with GOI. So anyone who is not feeling confident, even with our given confidence level, he can check the manuscript and he can decide. We have identified the area where we have found the association and so on. We have also provided a feedback mechanism. This is for our betterment of our tool. So if someone feels that a particular sentence, we got it wrong, the association should be positive, and we have got it negative, he can give that feedback. So we hope that if this is used regularly, then we will have a data set where the sentences will be manually curated, and then our pipeline will be able to give results with even higher confidence. We also want to incorporate drug trial information. I have also already mentioned that there are many drugs which are going through different trials and so on, and we want to provide periodic updates. In fact, Kaggle has released the second version of COVID-19 dataset, so our next immediate task would be to incorporate that in our website. And of course, slowly but steadily, the manual curation will continue. How much time do I have?
You have about 3 minutes.
Okay, thank you very much. So I will just give some acknowledgement first, because this is a collaborative effort with Hamad bin Khalifa University, where we have Dr. Tanvir Alam, which is a famous bioinformatician and so on. And I have to acknowledge various internet sources for images that I have used. So this is almost what I had to discuss, but I told you that I will come back to this slide, right? What we can do now. I mean, I tried, the main goal of my talk was to show that we have done something where we have used these sort of things, right? We have used ML, we have used the biomedical science and engineering, we have provided a tool and so on. And the main goal is to entice and encourage, particularly the student participants, audience, and the young researchers to do similar things, to do many more things. I'm sure that you will have 2 more talks where you will have more ideas. I will just end with one pointer that you should immediately go, if you haven't done so, here and check. I'm going to show you that if you go to archive you will see that, let me show you this. There are clear repositories for COVID-19 preprints. These are not reviewed, but if you go here, for example, you can get a list of papers that people are working on and they have submitted to the preprint, and most of these are under review. Some of them have already appeared in journals and so on. So this could be your starting point. You'll see a list of things that people are doing. Many of these things I'm sure we can do as well. Our students have all the talent to do that. So all our young researchers, I was discussing about what research questions should we ask. We will have idea about the research questions as well as about how to handle those research questions. In our last week's talk, I think Dr. Mufti provided a list of publicly available resources where we can work on. And he also mentioned that he is editing special issues. So you have the resources, you have ideas, and you have a venue ready to submit. So I think we should not wait. We should start working on it. If we have time, I can show you the website, but I think I'm running out of time. So I will stop it here to maybe if someone has questions, I can try to answer some of those.
Thank you very much, Professor Rahman, for a very enlightening presentation. The floor is now open for questions to the audience and participants. Please. Does anyone have any questions? I see some, Mrs. Sharmeen Sheila, she has raised her hand. Are you here? Sharmeen Sheila?
Hello, assalamu alaikum.
Yes.
Wa alaikum assalam.
Thank you, sir, for your nice presentation.
You're welcome.
Actually, sir, it was mistaken.
Okay, no worries, no worries.
Thank you.
Dr. Atikur Rahman Ahad, you have raised your hand. Please ask a question.
Thank you for the wonderful presentation and some research results as well. I found that, a good number of students or researchers, they are working on data collection, on different strategies, and make some kind of findings. So can you give some kind of information, if you know that, what are the impacts based on the current situation for those research topics?
Thank you, Professor Ahad, for raising this particular issue. I think this fits with my second slide very well. I mean, it should have been a coordinated effort between the government as well as the academia and the researchers to collect the data. I was mentioning to contact tracing, right? So contact tracing is an ICT application where we could have used the data as well from probably the telco data and so on. We always talk about the call centers, right? Because the hotlines, everyone is calling, and there were some interesting insights provided in some of the sessions given by the Health Directorate. How many calls are related to COVID-19? How many calls are related to something else, and so on? And from these sort of data, I think we can do magic. We can do many things. We can analyze the data. We can give the policymakers different types of indications and so on. In fact, there are other areas which are not directly apparent, which are not apparently related to COVID-19. For example, operational research. I forgot to add that in my circle. I mean, we are talking about, for example, we had this problem with sanitizers, right? So the supply chain, when we have a demand, when you have the supply information, and I'm sure that somewhere this information is available, even if in limited context. So if we had that information, we could have predicted what sort of inventory a particular shop or even the warehouse should have for these sort of things. I'm just talking about one example like hand sanitizer and so on. This applies for all sort of things, foods and other PPE, for example. PPE became a serious concern. I think now it has come to at some point which is somewhat acceptable, I guess. But I mean, there were a lot of things to do around these things. So yes, data collection, it can be like this. Many students tried. I am sure in the beginning, I also try to get involved in sort of data collection in different sources, like through SMS or through a Google Doc and so on. But for this to be meaningful, I think we should persuade our policymakers to make the data they already have available to us, the researchers, so that we can help them decide to formulate a policy.
Thank you very much.
Thank you very much.
The next question, Professor Sharifuddin.
Assalamu alaikum.
Wa alaikum assalam.
So I have a very naive question. You showed in your at the end of your presentation there are some confidence level. So how you prepared the metric for measuring this confidence level for example, drugs and others?
Okay, so this is not a very sophisticated method. I told you that at the end of the day, we use a neural network, right? So this was a deep neural network. We have used all the known things like Adam Optimizer and other things, ReLU and TANH and so on. So from a neural network, it is quite easy to get a confidence score. And what we had to do is we had to work with, it doesn't give you a confidence score, it gives you a score of classification. So if you get the classification score, and as well as because we had some other features as well, using those things, we came up with a formula to give a confidence score. So what does this basically means? That our classifier was able to classify a particular association, like say remdesivir and COVID-19 association, with high confidence. We call it in our case, it was 75% confidence, 75 point something. And for some cases, we have classified it to have negative association. And for that one as well, we have a similar confidence score, which basically means for the negative classification, we have very high confidence or low confidence. For the gene association, unfortunately, we don't have a neural network pipeline here, as you can see. So here, we could not give a confidence score. Rather, using the cosine similarity and the association with the gold standard data set, for the limited number of data set that we could match with this GenNet, we came up with an idea that this should be with minimum confidence. This should be that there is an internal score, but this is not really related to any classification score. Rather, this is related to cosine similarity, and somehow we divided it into 3 phases: medium, low, medium, and high. So does it answer your question, Sharif sir?
Almost, but from there are 2 medicine you just showed us. That is, one is 72% around, and the other is 60%. So those your confidence level is not so very it differs from each other. But how you can find the negative side effects? For example, more than 100 side effects, but other one is no side effects. So
no, sorry. Yeah, Professor Sharif. I mean, it's not that remdesivir didn't have any side effects. I'm not sure. I can check it right now before you.
Were we supposed to come, Professor Rahman?
His mic is off, so you can.
Oh. Okay. Oh. I think Professor Rahman might have lost his connection. I don't see him in the meeting right now.
By the way, just few moments ago, there were 113 participants. Suddenly it became 16. So is there anything? Can you check whether the connections or anything is all, I mean, missing, please?
Samin, can you look into this, please?
Sir, I just talked with Sohel, sir. He's trying again to join. Maybe there was some problem with internet connection. I'm not sure. We don't have any problem here. No, he's not here. Maybe it is an internet problem. He's trying to join again.
Okay.
Dr. Mustafa, all right?
Yes. Is Professor Rahman back? Okay. Should we still have 16 participants. Should we move on to the next speaker, or should we wait?
So there may be some technical problem. We have to check.
Okay.
I have a comment.
Please, please.
Just like,
Yes,
I mean,
sir.
as suddenly the number of participants and other things are not okay. So is it possible that you close it down and restart, or what to do? Because
Sir, everyone is joining. You see the numbers
okay,
rising.
Yeah, numbers are.
that means that, I mean, they are coming back. Okay.
Maybe there is some problem with Zoom.
Yeah, because suddenly it was
Suddenly
from
it was
113 to
16.
just about
Yep.
10. It is surprising. Anyway.
Okay. Okay, I think we can wait for a minute or so, and then if after that we can move on to the next speaker if it takes too long.
Professor Mustafa,
Yes.
I think you should move to the next speaker.
Okay, great. Okay. I apologize for the technical difficulties we're facing with Zoom, but so let's move on to the next speaker. We have our second distinguished speaker today is Dr. Supavadee Aramvith, who's with us today from Thailand. Dr. Supavadee Aramvith received her bachelor's in science, first class honors degree in computer science from Mahidol University in 1993. She received the MS and PhD degrees in electrical engineering from the University of Washington, Seattle, USA in 1996 and 2001, respectively. She joined Chulalongkorn University in June 2001. Currently, she's an associate professor at Department of Electrical Engineering with specialization in video technology. She has successfully advised 9 PhD, 27 masters, and 32 bachelor's graduates. She published over 130 papers in international conference proceedings and journals with 4 international book chapters. She has rich project management experiences as the project leader and former technical committee chairs to the Thailand government bodies in telecommunications and ICT. She's very active in the international arena with the leadership positions in the international networks such as JICA project for AUN SeedNet and the professional organizations such as IEEE, IEEE, APSIPA, and ITU. She's currently a member IEEE Educational Board Activities Board and chair IEEE EAB Section Education Outreach Committee. She's also a member of Board of Governors of IEEE Consumer Electronics Society from 2019 to 2021, a communications chair, IEEE Humanitarian Activities Committee, IEEE New Initiative Committee member. She also chairs Region 10 Sections and Chapters Committee and is the candidate for 2021-2022 Region 10 Director-elect. She formerly led educational activities and women in engineering for IEEE Asia Pacific Region 10 from 2001 to 2016. So without further ado, I'd like to give the floor over to Dr. Aramvith to give us her presentation. Thank you.
Okay, thank you very much. You can hear me, right? I will
Yes.
share my screen. Okay. Yeah, so is this my honor? Oh, sorry, is this not? So is this my honor to give a talk today to Bangladesh Section Computer Society Chapter International Series. And my talk today would be about the deep learning called capsule COVID-19, which is a feature detection of COVID-19 from chest X-ray images using deep capsule network. And as previously introduced, yeah, I'm from Chulalongkorn University, Bangkok, Thailand. And Chulalongkorn University is the biggest university in Thailand, oldest and most prestigious. It's ranked #1 in university in Thailand for 7 consecutive years by the QS World Ranking. So you can see the number of the faculties, academic program, student and personnel. Okay, so some of you, if you used to visit Thailand or you graduate from there, so you would know our university. And as I think I was previously introduced, so I'm gonna pass, this slide. And of course, I have several IEEE leadership position, and several of them actually have a call now for the special project for the COVID-19. For example, IEEE Humanitarian Activity Committee had a special call, but actually the deadline would be tomorrow, which is June 1st. And IEEE Foundation also have the special call as well for the project. And I believe Region 10 also have, but maybe it is already concluded. So you can try to find several of the opportunity, okay, so that we could have, of course, some funding to help contribute to solve several issues that has arisen by COVID. And my research is mainly on the video technology. So I give several talks about surveillance video analytics. So as of now we have an AI, machine learning, and deep learning, and it has been used a lot in the different application. And then for sure it can be used to tackle some of the COVID problem as well. So I have several work mainly on like a video analytic, like super resolution, face recognition, anomaly detection. And now most of them is mainly use the deep learning technology. And as you all know, deep learning technology is based on the multi-layer neural network. So if we have, vast amount of data, so it is possible, okay, to train that data and then use it to do the prediction, okay, of the real case data set. So in view on this, although my research is not directly related to the medical image, but we have the know-how in terms of the deep learning model. So I guess it is a good contribution. And today I will give some preliminary result that we did on the laboratory today. So when we do research, okay, so mainly research is the distance between an idea and realization. And this is a quote by David Sanoff. So he is the CEO of the Rio Corporation of America. So mainly he is the one who helped set up the NBC television network and was called the father of the the America television. And then I like this quote because mainly when there are because we are the researcher, and when there are a problem, of course, as the engineer and computer scientist, and as in terms of this, so we are think of something. Of course, with the technological background, we will have so many ideas that we would like to contribute, right? But depend on the experience, depend on the technology tool that's available, and depend also on the technical background that we have. From idea to the realization, it can be far. But of course, if we can do, we have more experience in research, the idea and realization would become closer. And I believe that in the case of the COVID, that today many researchers, government entity, around the world has joined force, right, to help that if we could have vaccine, if we could have some technology that help solve several issues related of the COVID. Okay, so the realization would come faster. So this is the figure that I took from the World Health Organization. So it showed the number of the COVID-19 cases report in the last 7 days by country. I believe that it's from last week, so this data is quite recent. So we can see like there are several of the country, almost all country in the world that has still the new case that report in the last 7 days. And then as we see the new, we can see that some country that already have the infection first is already phased out. Like for example, Thailand, we are in the single digit for like a month. And then it because we still have some of the Thai citizens that come back from abroad. So someday it would go up to the second digit, but we are still all right. I believe even now the government has relaxed the emergency measure, so that now it start on the phase 3. So it's mean like the department store is open and the restaurant is open, but we have still to keep the social distance as a great measure. Okay, so if mainly we are helping each other, so I hope that that every country would go to the yellow and would go to the white. Okay, so although it may take some time, and I do wish that the people in Bangladesh are with the safety and great help, and then we help each other to tackle the COVID. Okay. So this is like the statistic for Thailand. So the total is the 3,077 confirmed case, and as of yesterday, we have new cases found. So thanks like to the Thailand. So our country has quite a high index of the health security. And then we also have the very good medical facilities. So that's also, help a lot, but it also, depend on the factor, not only our country as well. So in my university, Chulalongkorn, of course, we have several of the faculties. So we have a lot of the research, okay, that we could think to fight the COVID. So this is the innovation from our university that now is currently, in use. Sorry, some of these are Thai, but I will just mention some, right? For example, we have the CU robot. we call the robo COVID. So we use this mainly to like send the food and then the medicine, okay, to the patient who got infected. We have the communication type of robot that could help record the vital sign, the pressure, the temperature, and also the communication robot that would be able to, have a distant conversation also with the doctor. Okay, and then our university we developed the COVID-19 strip test service, in which with this strip test you are able to know the result. Actually, the result would take only 2 minutes, but with you have to log in and sign in via your mobile device, and so on. So typically it takes like 10 minutes. Okay, so this has been used for our faculty staff and also in public, as well as our university also have the hospital. And then we have like the new style of the face shield, the shield plus protecting spray. The negative pressure box that have the HEPA filter, okay, that can kill the virus. And then we have the hydrogen peroxide, okay, that could spray out the VQ and VQ20 plus HP 35 that would expect to, of course, kill also some of the virus as well. We have the lung care application that mainly use the breath through the microphone input of the phone, and are at least able to tell the effectiveness of the lung as the pre-screening. And then also we have like a billing application that is the center point that the giver and then the one who want to receive the needer, okay, can come together. Okay, so that is some innovation from our university. Now let's come to what I will sharing today. So we all know that deep learning has been used in the medical image classification. So it's been in terms of the chest image, it has been in the research, of course, for a long time. So in this case, we've tried to add some of the data set on the COVID-19 chest image and try to see if the newer deep learning model, okay, it is effective to classify or not. So before I start, I would like just to show some literature review. Of course, COVID-19 was burst out in December 2019. So it's been, if there are any research related to it, it will now publish in 2020. So this is what we found about of course the similar work that has been used different type of the convolutional neural network, okay, for the X-ray to detect. Okay, so there are like this work that they use deep learning model with 17 convolutional layer, and some also use the CT image, okay, to screen the coronavirus disease. Okay, so in this case, they are successfully confirmed, the positive result as well. There is a work on the COVID-net, okay, that also used detect the chest X-ray image, okay, and this use the open access benchmark. And there are also the work on the anomaly detection as the COVID-19 screening. So they have the two category of image. Okay, one is the chest X-ray and one is the chest X-ray with the pneumonia. So this they separate between the COVID-19 and then the pneumonia. Okay, and they're using a pre-trained ResNet architecture. And there are some also other work as well that use this data set. That separate the pre-incident as well. And this is also the ResNet. So we can see that there are several of the work that has been published in this area. So we all know about, if you have background on the machine learning and deep learning, so you know about convolutional neural network. okay, that mainly we input the image and then it will go several layer, okay, of the convolution. So it's like a filter. Mainly, if for example, if you have 3 convolutional layers, so we can use that. I mean, like to extract, for example, the low spatial frequency feature, medium spatial frequency feature, and then high frequency spatial features. Okay, and then when it could extract out, okay, so we will train that. Okay, and then mainly we try to do the prediction, okay, so that we could be able to classify, I mean, the correct information. And of course, it would consist of the the training phase, validation phase, and also the testing phase. Okay, so while the general convolutional neural network learns statistical pattern in images, okay, but somehow they miss out to learn about fundamental concept. Okay, like if for example, if we have this phase, so of course, if from our eye, right, so we will know, of course, the left one is a face, and then the second one, maybe we cannot say it's a face. Also, we know that component that mean the eye, the lips, the nose, and the whole face are there, but it's not in the proper orientation and position. Okay, but mainly if you put this into the conventional CNN, it will return result that this two is a face. So Jeffrey Hinton, okay, so he is the one of the 4 which is called the father of AI, and with his student the Sarah Saber. Okay, so they invent the concept of a capsule network in 2017. Actually, a capsule network and then some of the algorithm, okay, exist long time ago, but somehow with the computational complexity at that time is not be able to apply, I mean, to the deep learning. So there is a study of the neuroscience that brain is organized into the module, okay, called capsule, right? So all of these capsule would be, I mean, good at the handling of the feature of the object, or we call the instantaneous entity. For example, like the pose, which relate to translation or rotational information, like a position, size, and the orientation, the deformation, the velocity, hue, and then the texture. Okay, so our brain will have mechanism, okay, for like routing this low-level visual information to the base capsule to handle it, and that would explain how we are able to tell in the previous slide that the eye and everything is out of places. Okay. So they proposed the capsule network and also the dynamic routing algorithm to tackle, okay, what the CNN is inadequate. Okay, so this I was referenced from the medium.com article. So if you can like scan this QR code, and you can go directly to that article. So in terms of the CNN, right, as I told you before, if we have this phase and we go in, then it will output as a phase. But if we put it into the capsule network, it will tell that it is not a phase. So what difference between these is that the conventional CNN has the property of translation invariant, and the capsule network has the property of translation equivariant. So if we give an example of this cat, so if you pass to CNN, it will just classify this cat. But capsule network, which has a translation equivalence, it can classify and tell further that this cat is located near the right side of the image, and then this cat is, I mean, sit near the left side of the image. So that is the additional information of the position. So if we would like to apply the chest X-ray image classification with the capsule network, okay, so this is just the example of the chest X-ray image. Okay, the top one is the person who have the pneumonia positive, and the lower one is the one that has the COVID positive. So if we put these two typical CNN, of course, it will be able to tell that they have a pneumonia. But if you pass through the capsule network, okay, so it can tell that have a pneumonia, and in addition, with the symptom on the left as well as the right lobe. And the same thing with down here, it can tell that it has the COVID positive with the maximum intensity of disease on the right lobe. So it means it gives a further information that would be more helpful in terms of the diagnostic of the doctor. So the capsule architecture. So mainly, I will just roughly talk about it. Okay, so mainly we have the standard convolutional layer here. Okay, that apply before the primary capsule. So this one is 9 multiplied by 9 multiplied by 256, and then it's go to the primary with the 32 channel. Okay, and then this dry of 2. Okay, and then also later, okay, it has some of the activation function called the squash function. Okay, and then later on is have the dynamic routing algorithm. Okay, so that this 32 output of the length of the output of this the digit cap vector, okay, could be result of the capsule layer in the third layer of the dynamic routing. Okay, and there is additional of the routing by agreement algorithm that will do the voting of the high probability. Okay, so make a base of the classification. And I mean, you can take a look of the paper in these two reference, but mainly this table show the difference in terms of the architecture between the traditional neural network in CNN and then also for the capsule network architecture. So our proposed the capsule COVID-19 network architecture. So mainly we have, of course, if we have design our network. So the capsule network itself, it has the pre-trained network, so called CapsNet. So you can also I mean download that. So that one will implement according to the paper. But this one we of course we follow some of the original capsule network, but then also have certain modification, because if we are able to design our own model and then inspired by other architecture, we can always make a change, or even I mean add in several layers or fine tuning some parameter. Okay, so it's better than if you use the pre-trained network. And then many of the research work now, they use the pre-trained network. So it means they may not be possible for them to change anything much. Okay, so if we feed the chest X-ray image in, it's go to the 3 layer of the CNN, which extract the local feature, which is the low frequency, I mean, which is like the edge and contour, and then the medium frequency, okay, which is maybe be able to tell like the I mean the eye, the mouse or something like that. Okay, and then the overall frequency. Okay, and then this go to the primary cap in which it is similar. We have a similar architecture. Okay, and then let's go to the routing agreement and full connected layer. So in this, I didn't go into detail to show some information in there because the research is still in progress. And then finally, we will have a 3 class of the classification, which is the COVID negative, COVID positive, and viral pneumonia. So in training and testing, So we make a reference to Kaggle data set, okay, which is the COVID-19 radiography database. And this is the link to the data set. Okay. So in this case, okay, so in terms of the training, we have 2019, of the COVID positive images, and then the healthy normal images of 1,341, and the one with the viral pneumonia is the 1,345. Okay. So we use the Adam optimizer and with this learning rate, and then 100 epochs because it has been tested after that the performance does not improve, and batch size is 8. But I mean, in this case, in terms of testing, we still have to acquire the real data set, which is now is difficult to acquire, because on this work and many other work, they still use the public data set. Okay. So it means like if we want to test, we would have to, mainly we do the random sample, okay, from the data set. So I mean, we do not specifically select which one, but we did random. Okay, so we did the random in the total of the 93, okay, and then the preliminary result show 96% accuracy that classify into the lung of people who are normal, and then the lung of the people who has the COVID, and the lung of the people who have the viral pneumonia. Okay, so and then we, of course, our work is still ongoing, so we don't have the confusion metric, I mean, to show the accuracy of overall yet. Okay. So for the conclusion, okay, so we have shown that the preliminary results show the capsule network is a possible choice for medical image classification. And we have a case study of the COVID-19. Okay. Still, we have to do more investigation, I mean, to utilize the instantaneous entity, which is a several feature, okay, such as like the orientation and the location and several other things that would contribute into a better detection and then extract more information of the lung infection. Also, more training and testing in the proposed method for the conclusive output. And normally, because capsule network, it can extract extra information that the conventional CNN does not. So it means that it would consume more processing time than the conventional CNN. Okay, so we also have to optimize the model for the faster processing as well. And as the deep learning classification shows the promising result, still I think we have to think about, not we do that it's just for the publication, right? So it means we have to think how we could integrate this, like how doctor could use it, like for the pre-screen and so on. If there are like so many cases and they don't have like enough doctor now to interpret the result or to pre-screen, right? So this has to be, I mean, under discussion also, not only to the engineer, but also include the stakeholder like a doctor or the university and so on, of how we could use this, because we all know that to diagnose the COVID-19 patient, you need the several of the symptom into cooperation as well. So that would be the end of my presentation. And it's just like at Chulalongkorn University, we have several scholarships for the PhD and postdoctoral fellowship as well. Okay, so we have several types of the scholarship, and the postdoc, which is have an industrial postdoc, senior postdoc, I mean, as well. So if you need more information, you can contact me. And if you have also question about today's presentation, I welcome you to also connect me via Facebook, via LinkedIn, send to my email. So thank you very much for your kind attention.
Thank you very much, Dr. Aramvith, for a very enlightening presentation. The floor is now open to questions. Questions of anyone? I see Dr. Shamim Kaiser raising his hand. Sir, please ask your question. Dr. Shamim Kaiser?
Hello, can you hear me?
Yes.
Okay, I have a question to the speaker. If we compare CNN with the capsule network, in my opinion, it should be computationally expensive, or the cost will become high. So how we can actually handle this issue?
I mean, the capsule network would be more computationally.
Yeah, computationally expensive
Yeah,
than
yeah.
the traditional one.
Yeah,
So,
so I think one thing we also have to see what kind of the feature that is really related. I mean, to for the lung classification, what information that we want. Of course, like the location would be useful, but maybe other things that we can optimize by reduce certain parameter. So we are investigating this as well.
okay, thank you very much.
Okay. Does anyone have another question? Yes, Dr. Atikur Rahman Ahad, please.
Yes. Thank you for your wonderful presentation. My question or query is that, I mean, there are not only the Kaggle, few other smaller personally collected data sets on X-ray data, but I'm not sure. I didn't check the Kaggle one, but do they get the doctor's information at the same time based on different other things? Like a patient can be COVID affected, but at the same time, some other lung-related diseases or so on. So based on those information and doctor's data, or age or other issues, is there anything, I mean, more detailed on those data sets? Because this is one, and then I mean, next one is related to this, that the number of samples are really tiny, considering, I mean, CNN models or others. So any possibilities on COVID cases that have previously introduced many handcrafted features can be suitable or usable at the same time, because we don't know that the real, I mean, we don't know the exact scenario. So just if you can give a little bit more about this. Thank you so much.
Yeah, I think the first question about the data set. Yeah, of course, I think when it's labeled, it's supposed to be already confirmed by the doctor. But I mean, I think the medical doctor can tell best, because if like we are like a non-medical, it's very difficult to, if we can judge by the eye, we cannot see the difference between the lung of those who infect with pneumonia or the TB, right? Or other kind of disease with the COVID, right? So I think this also, I mean, so in terms of this classification is may have to include the lung of the people that infect from other causes, like here is not include the TB. Of course, the TB has a symptom of the pneumonia as well. So I think, this could be, I mean, one issue. And I think your second question is like the handcraft feature, right?
Yes, please.
Yeah, handcraft
The second
features.
question is,
I think this type is because all the CNN, the tools are already there. So I think like people just like first, many of them that they do it, they just try with the CNN because it have a capability when it's learned from the feature of many data set, then it can make a accurate classification. Because it in terms of handcraft, I think there are, of course, there are many work behind that, but I'm not sure that it can classify without the example. Yeah, so that would be my answer. You have only 2 questions, or you have more?
no, maybe some others have.
Yeah.
So
Yes, so we have another person, Ajwad Akil. He has a question.
Yeah, thank you for the floor. I'm actually an undergrad in computer science. So my question is that can we use autoencoders to gain more suitable features before we pass the features for classification?
Because actually they also call capsule network somehow of the similar to autoencoder as well. I mean it architecture. So that's why it can extract, I mean, more feature that CNN does not have. Yeah.
Yeah, thank you.
All right. I have a quick, does anyone have any questions anymore? I had a quick question. Since we have a lot of students in our audience, and some of them who might not be familiar with machine learning as much, Dr. Aramvith, could you just give us a quick overview with this stage of the pandemic, where we are actually in the middle of the pandemic, there could be a potentially second wave, and the drugs are not there yet, vaccine development is underway. Where do you think we can use machine learning most effectively at this current stage in the middle of the pandemic? Where do you think currently I'm sure there's many options, many different avenues people can go into, but what would you think at this point would be most effective?
You mean relate to the scope that I talk?
Yes.
Yeah, I think in terms of the classification, it can use incorporate with the doctor decision, because as I mentioned, if we need to like do the pre-screening, this also will be useful for the pre-screening. So I mean if in case of the cooperation with the doctor, I think it would be useful and can use right away in terms of the pre-screen.
Okay, yeah. Thank you very much. So I'd like to thank our speaker. We are running out of time, for giving us a great presentation and also enlightening us with answering our questions. I'd like to hand over the stage over to Dr. Kibriya to introduce our next speaker and moderate the next talk. Dr. Kibriya.
Thank you, Dr. Mustafa. Now we have our last speaker, and we have Dr. Mohammad Enamul Haq Choudhury. Dr. Mohammad Enamul Haq Choudhury received his bachelor degree with record marks and master's degree from the Department of Electrical and Electronics Engineering at the University of Dhaka, Bangladesh, and PhD degree from the University of Nottingham, UK, in biomedical instrumentation. He is currently working as a faculty at the Electrical Engineering Department, Qatar University. He is a recipient of prestigious Commonwealth Scholarship from British government during his PhD study. He worked as postdoctoral research fellow at the Sir Peter Mansfield Imaging Center in the University of Nottingham, United Kingdom. Prior to joining Qatar University, he worked in several universities of Bangladesh. His current research interests include biomedical instrumentation and signal processing, wireless body sensors, artificial intelligence and machine learning, embedded system design, and simultaneous EEG fMRI. In these areas, he has published more than 50 peer-reviewed journals and conference papers. Dr. Choudhury has been involved in several NPRP, UREP, and QU internal grants, academic and government projects, EPA SRC and EPSRC ACC, along with national and international awards. He is currently running $2.5 million worth several QNRF and QU grants. He has worked as consultant for the project entitled Driver Distraction Management Using Sensor Data Cloud. He has received ISIF Asia Community Choice Award 2013 for project entitled Design and Development of Precision Agriculture Information System for Bangladesh. His team has recently received COVID-19 Dataset Awards, due to their largest open access dataset on COVID-19 X-ray images. Now I welcome Dr. Mohammad Enamul Haq Choudhury to present. Thank you.
Thank you, Mr. Mustafa. I hope you can see my presentation now, yeah? Okay, thanks for the organizer for organizing such a nice event in this COVID-19 situation, and all world is stuck actually. And today I will be presenting as a last speaker in the event of IEEE VDC second session of lecture series. And the topic is fight against COVID-19 pandemic using machine learning. And I'll be talking about actually some robust COVID-19 detection techniques using clinical data or the radiography data, which is very close to the previous talk. And thanks for introducing and talking about me. I'll just move into my topic. Okay, so I will briefly talk about the different updates about COVID-19. I think most of you are aware of that, but I'll quickly go over it. And then I will talk about my recent few papers which are under review right now. Like one of them is, can AI help in screening viral and COVID-19 pneumonia? And then I'll be talking about can actually we distinguish SARS, MARS, and COVID with the help of AI, because doctor cannot differentiate by their eyes. So, but can AI help that? And then we will be talking about like how transfer learning can help us in investigating COVID-19 diseases. And then last but not the least, comparative study on early detection of COVID-19 from the chest X-ray. And then I'll talk about what are the current works we are carrying out and what are the potential works we can contribute and collaborate as well. Okay, let's move into the updates. So if you look at the table, I know a lot of people are regularly following this, but you can see the number of confirmed cases and deaths and the percentage of death in from the country, and then numbers per million, cases per million, deaths per million. If you look at these numbers, there is nowhere we can see the name of Bangladesh in the list. And the list, I was presenting a couple of days back in India, and I was showing that India is quickly getting to the top in the list, and Pakistan is also, you can see there, but luckily we are not in the list because of the number of infected people in the country. But I feel this is not because the number is small, rather because of the test is small, less. We are doing less number of tests, but the good thing, of course, the death per million population is alhamdulillah less, which is one good side. But there are some other graphs I'm going to show. So if you look at the average deaths in the different hotspots, so you can see some countries are actually moving towards the peaks and some countries are declining. But still, you cannot say about USA clearly, but some countries definitely, Italy, for example, is declining. But some countries are moving towards again, because you can see France, it was declining and then moving again. So Brazil is going towards the peak. So if you look about the rising and falling in the cases, that is a really important point for Bangladesh perspective. You can see the name of Bangladesh is appearing here in the red side, which is the rising case. And these countries are in the falling case. These countries are managed to tackle the situation, and their curve is now flattening. Whereas in our country, the curve is raising. So although we are not like the France or other countries, big percentage, but still it is rising. If you look at the number of deaths per week, we can still see the number of name of Bangladesh here is. So these two are the alarming things for us. In the last couple of weeks, we can see the number of rates and number of deaths are increasing significantly, which is saying we should take precaution. On the other hand, we can see government is relaxing a lot of things, which can cause a really, really big problem for our country. Okay, so let's quickly move into the situation. Do we need to panic in COVID-19, or we can think seriously, or we can think about the population age and their other issues? So if you look at the percentage, based on 22nd May's data, we can see 80% or 81% population of the COVID-19 infected population is actually mild, like simple flu. So they can stay home and do their normal resting and take enough hydration and normal plenty of foods, then they can survive probably, they can recover. And that's the statistics says in from the last few months. And the severe, this percentage, like 19% is actually the severe case. Those need to be taken to the hospital and should be taken proper care, especially ventilation or ICU. And if you look at the risk factor in terms of the age, we can see is from Italian and UK data, and UK is a significant number, you know, and Italy has also significant number. From these two countries data, you can see less than 6 or you can less than 50 is less dangerous. If you are somewhere here, you can you have to be careful, but you should not panic. COVID-19 doesn't mean that someone will definitely be in a panic situation, but rather we should focus on the red areas people. If they are infected, then hospital support should be should take care of this population more. And if you look at the in terms of existing disease condition, so you can see if someone doesn't have any other disease condition, like we say comorbidity, so that this is only 9.9%. But other cases, someone has cardiac problem, diabetes or chronic lungs disease or blood pressure or cancer, then this population is seriously affected. So also for the doctors and hospitals and also the government policymakers, they should focus on those patients who have these problems. And in terms of the gender, if you look even Bangladeshi data, every day I'm following the news papers and online news, I can see the population in Bangladesh percentage in male and female will be even less. You will see the percentage maybe 10 to 90 or 20 to 80 in Bangladesh. So it's a world data. So you can see it's in UK and Italy, this is 37% women and 60% male. So you can see even here, male should be more prioritized in treatment because they are showing more like death percentage. So let's look how contagious this disease and should we need to be very careful or not. We know it's a very contagious disease, and what if we compare with other diseases? Like if you look at the Ebola, MERS, they are much more contagious and similar contagious, but much more percentage of death was very high. If you look at COVID-19, it's very similar to the Spanish flu, which happened in 100 years back, like 1 century back. But of course, the problem is the R naught factor, we say always. Although it's very difficult in this stage to finalize the number because in this number is very unreliable in this moment. When the situation will subside, then we can exactly figure out the number. But it is somewhat very close to the swine flu and other seasonal flus. But it's not like the MERS or the Ebola. So it is contagious, but not at the level of other such like diseases. And the other thing, which is very severe for us to consider, is this one. You can see the number of deaths, like and per million is our average population per day. How many people are dying per day? And these numbers are actually during pandemic, and other white numbers are other than pandemic, normal situation. So you can see COVID-19 was a few days earlier, even COVID-19 was behind here, but now it's climbing really up. So every day the average number is increasing. So it can even become the top of the list, which is the problem. If it lasts for a few months or few years, then the number will be really, really high if you continue this rate. But if the number stays, but if the number like the disease stays, but the death rate reduces, then of course it will come down. So that's these are the few important points I wanted to discuss before I want to move into my topic. So today I'll be mainly talking about how we can actually help or how we can utilize machine learning in fighting with COVID-19. So I start with, from my previous work. What is the problem right now? So if you look at the best techniques, so people are using all over the world, the RT-PCR, like the most widely used technique in the lab. And I've shown here the steps of how they do. They take sample from the respiratory specimens, and then from the there are some lab steps go through, and then the results come out. So it's a manual, complicated, and then time-consuming process. With a success rate reported in some paper 63, some less than 63, even 30, some documents. But the cost is very high, and of course requires specialized lab and specialized person. So if we compare with this with other technique like X-ray, CT, although there are a lot of concern come out from the World Health Organization and some of the like radiology societies that you should not use CT directly for COVID-19 technique detection. But we know in this particular situation, when the resource become very scarce, and especially if people are infecting in a large number, then we should look for alternative solution. That's why we started our work. And when we started our work in the beginning of February, there is a scarce data set, like there is no data set shared in the online internet. And first time we found out that Italian government, like Italian research group, SIRM, has shared a data of 60. Like they initially started with 40, then they move into up to 70. Now it is up to 80 data set, patient data with X-ray, CT, and some clinical data they have shared. So we took that task, and there is a nice initiative in GitHub from Dr. Cohen from Canada. He took initiative to collect some data from different articles, pre-printed articles and published articles, to create a database. So me and my group took this seriously, and we collected from whatever available in the internet with RT-PCR positive. Whenever they mentioned RT-PCR positive in the papers and online resources, we collected, and also utilize the community-acquired pneumonia dataset from Kaggle to create that dataset, and this is available in this link. And in our previously public dataset, we got 1,340 on normal image and 219 COVID-19 positive images, and these are viral images. So these are already confirmed by the doctors. So, and we received the award of COVID-19 dataset award because of our contribution to the Kaggle. And this encourages us, and we continue to build our database. But I will show first how this small dataset, even though the normal and pneumonia dataset is not small, but the COVID-19 dataset was slightly small. We did our initial work, and we use transfer learning. Those who don't have idea of transfer learning, I can quickly talk about that. You can see normally in MATLAB or any other platform, researchers, what they did, trained on a large data set, like for example ImageNet, the millions of images. They trained the large network with a powerful machine, and it is trained for very large number of classes. For in this example, I have a large image set, and I trained it for example a large number of classes. And then if we can, if we don't have that a large number of images for training, what we can do is in transfer learning, we can just take that train model and we can modify the final layer, the softmax layer, and then we can train it for a utilize it for a different problem domain and different number of classes, and it's actually showing promising result in different disciplines. So that's why we took this option. Then you don't need to train from scratch, and you can work with even small data set. And of course you can free some of the layers so that the whole network don't need to be trained again. So it can be faster, and you can of course do data augmentation, especially with a smaller data set. So what we did, of course, we use another researcher, I think already 50 or 100 papers published in X-rays. When we submitted in 29th of March, there are only few, 2-3 papers published at that time. But now hundreds of papers are available now. So if we see here, the confusion matrix, initially we used 130 training data, and we augmented it to 2,600. And then we completely test on a blind data set, like complete blind 60 data set, subject data. And we found that only 2 images our algorithm failed. And we got a very nice accuracy and sensitivity and other matrices. So we are really encouraged on this with this. And I have just showed here how good the network was working on a small chess set. So, And this is, along with this, we also observe that, as Dr. previously, Dr. was showing how we can specify machine strain from exactly in the correct area. So we actually observe that in the deep layer, we can find out the strongest channel, which is contributing for the classification. And we found that in COVID-19, there are some areas are shaded with, like you can say, it's a different whitish region identified by the feature identified in the deep layer, whereas in the normal images, there is nothing like that. So COVID-19 images has something different signature in the lungs, lung areas, which machine can learn from, which is not present in the normal. And we have seen that this is actually true. For a normal, you see, this is the deep layer image, and this is even more deep layer images. Can clearly see COVID-19 has different signature in the lung area. And viral pneumonia, which is another type of pneumonia, of course, not COVID-19 pneumonia, community acquired pneumonia due to other viruses, not COVID-19 viruses. You can see the distribution in the lungs are completely different. So machine can actually learn very well from these images in the deep layers. So this actually encouraged us to work more on this domain. So I have shown here two misclassified images. You can see these two images was misclassified by the algorithm, and we check with the doctors whether these are actually COVID-19 and our algorithm is missing. And doctors said they are very early stages of COVID-19. There is no symptom of COVID-19 in the lungs. That's why we believe network is missing that. So network is not missing any actually COVID-19 which has good amount of good symptom. It is actually missing when there is not that much specific symptom is present there. So then we thought, okay, why not we try what's the difference between COVID-19 with SARS and MERS, the previous COVID families. So, you know, SARS is in 2002 and 2003 outbreak in China, and it was appeared in 26 countries. And then MERS was outbreak in 2012 and 13, and it was most limited in Saudi Arabia and South Korea. And but that mortality rate was quite high in MERS and SARS than COVID. So we took, we looked for data. Then we found the same problem. There's no data. So we did, ourselves created the data set for COVID-19. We have already, by this time, we had 423 COVID cases, and we had 144 MERS and 134 SARS. And this is the largest data set online, which will going to be public. We'll going to make public very soon. Like our paper is submitted yesterday to the Nature Machine Learning. We'll make public once we got the approval from Nature. So now, if you look here, we found that in straightforward machine learning approaches, transfer learning algorithms suffer because they have very similarity in the lungs areas, because both are all are due to the COVID families. So we did some pre-processing. We apply original data, you can see histogram equalization and histogram of the histogram equalized data, and then CLI. We found there are some saturation occurs in the images due to histogram equalization. So we move into contrast limited adaptive histogram equalization, and we found that is doing super for actually histogram equalization for X-ray, because there's no saturation occurs here. So we tried other techniques, like in hospital, doctor used to use image complement techniques for looking in the image. So use that image processing technique as a pre-processing technique as well, and see how it works. So, and then what we did, we combine these three images, because all three are grayscale images, and CNN can take 3 channels. We feed 3 of these images to the 3 different channels of the CNN and try to train whether machine can learn something new or not. And we, of course, use this number of samples, this number for training, and after augmentation, it was like this. For validation and testing, we use this number of sets. After testing 18 different MATLAB pre-trained models, we reporting here only 4 different 4 best performing models. So you can see for the original images, Inception is performing best, but the DenseNet and ResNet is very close, but SqueezeNet little behind. But if we do the CLI equalization, then actually all networks are very close. So slightly SqueezeNet bad, but all networks are close. But we are not gaining something that much if we only use CLI. But if we use image complement, then we found that actually deep layers, deep networks like Inception, VT, and DenseNet are very large deep networks. They are doing very well, whereas ResNet is somewhat similar, but SqueezeNet is a shallow network, completely fails. But if we combine these three techniques and apply to a CNN, then we found actually there is a boost in the result performance in Inception. It's a very well performing network, and also we got some boost in the ResNet, but DenseNet and DenseNet didn't do well. It actually degrades, but SqueezeNet is not losing because it is already lost here quite. So by this technique, we are getting similar performance of the original in the SqueezeNet, but Inception is doing really good. So we then compare, okay, out of these three classification using four different techniques, which one is best? We can clearly see that overall performance of the 3-channel technique is superb. And only out of 423 images, this is the last highest comparison. If you see in the literature, so many images, COVID images we compare, here only 2 images is misclassified, as one is SARS, one is MERS. And in the paper we explained, this is the paper link, you explained everything why they are misclassified. But we found 10 images are misclassified with very high confidence by the network. So we can say there are some similarity between COVID, but these images are misclassified with less confidence interval. So we say these are like network was doubt because of the similarity in the pattern. So we can say actually from this result, AI can classify these 3 COVID cases with very high accuracy. You can see from the result. Then we move into a different experiment. Why shouldn't we try then? What is the best method or best algorithm for classifying COVID-19 type or X-ray images in out of the available data pre-trained models in MATLAB or Python? So we tried in MATLAB. By this time we gathered this number of vectorial images, this number of COVID-19, and this is the largest, second largest, you can say. By after this work, we even managed to increase our COVID-19 cases. So we have 1400 plus viral, 1500 plus normal, and 400 plus COVID and vectorial pneumonia images. Then we tried all the pre-trained models in MATLAB, and they have different depth and different size and different number of parameters, you can see. And we tested, and here we summarize our results so far, what we have managed. So we can clearly see, if I move this one a little bit left, the overall performance, if we look, the best performance for this X-ray type of problem, we found ResNet 101. And DenseNet and Inception are not that bad, but the best performance you are getting from ResNet. So I'm moving towards my presentation. I think I can answer your question at the end. So then we thought, okay, let's, why not we should utilize machine learning approach to early detect COVID-19. When doctor cannot understand even of symptom, they can say, okay, this can be pneumonia, this can be COVID, but RT-PCR can tell us after a few hours, but by this time, this patient can contaminate other patient as well. So we try to design a early detection technique for using COVID, chest X-ray images. So we use conventional transfer learning techniques to extract the feature, and then we feed this feature to our recent work, convolutional support estimate networks, CSN networks, as a compact network. We feed this feature to classify, and we found actually like these are the classical approaches. You can see CSN is performing very well in early detecting. Here we have normal and COVID case, and COVID is very early stages of COVID. Even doctor says these images are not COVID, although these are RT-PCR positive. So, and we found that actually CheckSnet, which is one of the deep learned network from X-ray images, is showing very high accuracy, but this very deep, really deep network, and this is dense network is another very deep network, and ResNet. So these are really deep network, but if you compare this one is very shallow network, but it also can get reasonable accuracy if we can fit feature. So that's our finding. These are the few missed cases. If I allow time later, I can, I don't know how many minutes I have left. So I can discuss later. So finally, we are working on segmenting X-ray images because, you know, to train properly, you should have the lungs. And I have a collaboration with Netherlands organization, and they have designed a software for finding out the probability score of the COVID along with the lung infected areas of the lungs. So we have managed to segment the lungs, and from the segmented images, we will classify, and of course we'll train and classify and give the probability score for the COVID. And then apart from these works, we are currently working on detecting and quantifying COVID-19 infection based on the previous work I showed. And we're also trying to combine X-ray and CT to show that some researchers claim that X-ray cannot do the job, but CT can do the job. But we want to combine these two study and show that X-ray can also do a great job in terms of classifying the COVID and non-COVID patients. And of course, we are parallelly working with the clinical data from the hospitals. We got a collaboration from China, and we are trying to also collaborate with the DMC and NHS in UK. So I got a large data set from 375 patients from the clinical data, from entry to the exit of the hospital, all clinical data. So we are working on the prognostic model. And then parallel, we're also working on a Russian database we got to grade the COVID-19 severity using CT data, like how they're progressing. And thanks for listening. I hope I have finished in time. Can you hear me?
Yeah, Dr. Aramvith,
okay.
Have you finished?
Yeah, I think I've finished, yeah.
Okay, thank you very much for your nice presentation. Now this is the open floor. If you have any question, you can ask. Okay.
Yeah, I think Dr. Atik wanted to ask something.
Yeah,
okay, thank you very much. Actually, Anamul is my direct classroom student. And this is the second time I am listening to him. First time he gave a lecture only for a few minutes in the fourth year final presentation time, early stage. And I'm very, very delighted and feeling really proud of him that he has been working on so much and so smartly and excellently. Wonderful. Now I have two tiny questions that will come. So number one is that, I mean, you mentioned, but again, you would like to clarify regarding all the data sets that most of the cases, X-rays are taken at the early stage. And another point is that not all positive cases, they have lung-related problems because they don't have cough or no breathing problem and so on. So is there any anything that can differentiate this kind of point? This is number one. And number two is that I'm working with, started working with the hospital regarding this early stage. So the doctor we discussed said that before proceeding, the X-ray gives some kind of data. Based on these, doctors can look at the X-ray sheet and then make some decision and then go for the further screening if PCR when PCR was not available or not possible and so on. So would you please give a little bit more on those issues? Thank you so much.
Yeah, thank you, Dr. Ahad, for raising these nice questions. Yeah, one important point is, you know, I believe in UK and also in other European countries, they are regularly using X-ray for like initial screening and also monitoring the patient progress, because, you know, CT is difficult to use during this pandemic situation, especially the hospitals are crowded and the patient is really difficult to take the patient to the CT room. And there are a lot of precautions they need to take for taking patient to the CT, whereas X-ray can be taken to the patient bed. It's a portable system. So that's why X-ray is popularly used in most of the European countries. And I have collaborator from Cambridge. They say they are using it regularly in the hospitals during the patient progress. So it's not early stage. Rather, it is used if you look at the Italian data set, I shared the link. You can check that one. They are sharing data of the patient in different days. When the patient even in severe condition, they are using X-ray for monitoring the patient. So X-ray are used in different days, not early numbers. And I can say you, out of our 630 images, we have only these images. These numbers are around 200 images are early stage. All 400 images are later stage images, like mild, moderate, and severe. These are, or using the moderate and severe. These are mild and no symptom at all. So first thing is we do have data with moderate, severe cases, and we also have very few symptomatic and mild cases. This is the first thing of your first answer of your question. Is that okay?
Yes, please. Yeah. Thank
Yeah.
you. Next.
Okay. Yeah. Second question regarding early detection. We have been working actually on this since, as I mentioned, beginning of February. Like last 3 months, we are day and night working on different aspects of this X-ray images in our different groups. And out of our all experiments, we can claim now that actually X-ray works super in COVID, like detecting COVID-19 even early stages. And the result I'm showing here, this is going to submit in 2 days transaction in neural network. So this one even shows that early cases, when doctor classifies these as very less or no symptom at all on the COVID X-ray images, but AI can identify them. So I believe the hospitals in Japan, definitely they can utilize models, train models, whether we provide or you train yourself using the models we are using in Python or MATLAB. Both ways are fine. You can train the compact models so that the doctor can just put their images and get the information immediately. And the work we are doing right now, that can even show the doctor the progression of the disease over time. That is the one area we are working now, how the X-ray can track the progression of the disease in the lungs. Hope that answered the question.
Yes, thank you very much. Just one correction that the hospital I am engaged now or trying to work on is not in Japan, it's in Bangladesh. So
okay, that's great.
That's why we are concerned, because developing countries, we don't have the PCR issues and easily, and X-ray and first detect and so on. So this kind of things. Yeah. Thank you so much.
Oh, that would be great. Actually, we will be really happy to collaborate in this kind of situation, because we have the tool, and I'm trying hard to collaborate with Dhaka, like DMC and also Kuruital Hospital. But of course, you know, apart from Bangladesh, if you're staying outside and working outside is difficult. But if you're working there, it will be probably easy for you to collaborate with the team. We are really happy to collaborate.
Oh, okay, thank you. But again, I am now in Japan, but I'm trying to manage the difficult task, as you mentioned, from Bangladesh, and I'm working. So I'll knock you later, maybe, or you can knock me, so we can find some time to discuss further to find some modalities to work on. Thank you so much.
Thank you.
Okay, thank you, Professor Ahad. Anyone else to ask any question? Okay, I just want to inform one thing, that at the beginning we had almost 130 plus participants in this webinar. Actually, almost 40 participants are now listening, but they are in separate instance. This is one instance. This is the main instance where the presenter and the host, they are in this group, and there are another group, almost 40 plus participants are listening, but we are not watching them in the list. Okay, so maybe this is the, there is no one, but I have one question to.
I have, okay.
Okay, Professor Atikur Rahman, please, you complete.
No, please go on. Yeah, after you, I can ask. Okay.
Okay, one thing is that chest X-ray is the imaging technique that plays an important role in the diagnosis of COVID-19 disease. However, due to the limited availability of annotated medical images, what are the challenges for classification of medical images in diagnosis?
Yeah, thanks for your question. Yeah, actually, if we say due to the limited availability, then I should say if you are mentioning COVID-19 limited availability, then it is true. COVID-19 images, we have very limited number of less than 1,000, of course, COVID-19 X-ray images. But if we say medical images, X-ray medical images, that's not true, because, you know, NHS shared 100K leveled images public. So it is available. And Stanford shared more than 260K, sorry, public leveled images. And Italian government, there is a Italian organization who shared actually 126K leveled images for X-ray. So we are utilizing this. But the problem is COVID-19 images is scarce still. If we have hundreds of 100K images of COVID-19, 100K normal, 100K viral, then we can train a model directly from scratch. We don't need to take the help of transfer learning. We don't need to directly take help of image augmentation. Then we can make a really reliable model. We can say, okay, that's the model that can work standalone. But definitely we are missing COVID-19, but we are not missing with viral and normal images. Initially we were thinking that, but then we got all the images. We have now 3 databases which are thousands of images are there. If you need link, I can share.
Okay, thank you very much. So Professor Ahad.
Thank you so much. You mentioned in the conclusions or other current works that you are trying to engage X-ray and CT and their combinations. Yes. This is number 1. And also the grading of the patients based on their severity from CT data. Yes. Just there are almost no work I found. So this is very interesting. So would you please give some more information about this, and how did you get the city data? Or
yeah, actually we got I have collaboration with, thank you, Dr. I got I have several collaboration international right now for COVID-19. One is with Cambridge University, and other with Italian Institute, and one is with Netherlands Institute. So I got data set also from Russia. I got data set from Russia that has 1,100 plus COVID-19 cases, and among that all COVID-19 patients, so it's a volume, CT volume, so each patient have at least 30 or 40 slices. So and these images doctors has classified as severity 0, 1, 2, 3, 4, 5. So we will train the network using this COVID CT images, and then we classify them. Of course we will use segmentation, lung segmentation.
Okay, thank you. May I ask one more question?
Please, yeah.
Okay, so we know that China is extremely good in computer vision, AI, machine learning, this kind of stuff. As it, attacked China at the beginning, and they did a lot. So do you know that, they have some very good data set, or they are doing something good research on these, or is still not published, already, something like that? Any idea on that? Because they should do much more.
Yes, they did. Yes, Dr. Adi, you are right. They did. Actually, if you look at the X-ray domain, and if you look at the CT domain, you can see I did all the work. We did all the work on X-ray, because when we started work, China already published 10-20 paper on good journal, especially radiology and biomedical transaction and machine learning areas, good journal papers. They already published their 10-20 paper on CT. And then if you stand now after 3 months from our point, 3 months and a half, then they have published around 100 journal papers on CT, very high quality works, very good number of images, and they published already. So if we start work on CT at that moment, we could not do anything, because they already have large data set. We don't have any data set at that time. But we started with X-ray, and by that time, 3 months, we got some good result on X-ray, and we shared the data set in Kaggle. After us sharing the data set, at least 20-30 new paper came. And I think the Thailand doctor from Thailand, she was also mentioning that this is our data set. This is the largest data set still now on COVID. And we are going to publish another 2 days data set very soon, inshallah. And that will be the largest data set. If no government come and share, and a hospital come and share, they are not sharing. We are trying hard even from Qatar. We have 50,000 cases in Qatar, but we are not getting data from Qatar. Very, very strict. Every government is strict on like holding the data. But of course, Chinese government Chinese team has shared data and then published a paper in Cell journal. We have access to the data set. That is a large city data. And of course, we can collaborate. If you have good team, we are actually have a lot of ideas, but we are struggling with computer capability and team members. I have 7, 8 masters and PhD student total working together and others working together, but we are suffering of the limited number of manpower on this. We need help.
Okay, thank you so much. I can provide some brilliant students and we can cooperate. Thank you so much from my side. Wonderful.
Okay, thank you, Professor Ahad. Actually, as I told that more than 40 participants are in separate groups, but I don't see the hand raised. That's why thank you very much. And thank you, Professor Sohel Rahman. Thank you, Dr. Supavadee, and thank you, Dr. Enamul Haq, for today's lecture. And now I hand over the mic, Dr. Mustafa. Thank you very much.
Thank you, Dr. Kibria. We have come to the end of our lecture series today, and I'd like to thank the organizers for organizing this very enlightening lecture session to us. Specifically, we're thanking the IEEE Computer Society Bangladesh Chapter, the IEEE Computer Society BUET Student Branch, the IEEE Computer Society BRACU University Student Chapter, as well as Team Spark for helping us organize this. I'd like to also thank Professor Sharifuddin, who was our past chair of IEEE Computer Society Bangladesh Chapter, to be with us actively here today, and also for the leadership shown by Professor Abdul Razzaq. Last but not the least, I would like to thank our speakers, Professor Dr. Muhammad Sohel Rahman, Dr. Supavadee Aramvith, and Dr. Muhammad Enamul Haq Chaudhary, for giving us their valuable time and their insights into this big problem that we are facing currently today. And before I leave, I'd like to let everyone know that the third lecture in this lecture series is going to take place on 7th of June at 3 p.m. Bangladesh time. I would like to request all interested parties to please register for this event via the registration link that will be provided in the Facebook page of IEEE Computer Society Bangladesh Chapter. Thank you all very much for your participation and your time. And from IEEE Computer Society Bangladesh Chapter, we're signing off. Thank you.
Thank you.